Loan.
Okay.
Organizers will give an introductory note about you, sir. After that, in another 2 minutes, we can start our session, sir. Arun?
Yes.
Yeah, you can go ahead. You can go ahead.
So, good evening, everyone. Myself, Dr. Arun Shekhar, Assistant Professor, Department of ECE Geometries, convener for this 6 days International Faculty Development Program on Technology for Social Relevance, organized by Department of ECE Geometries, Rocham, Andhra Pradesh. So, I feel privileged to welcome you all for this third day of the 6th session of this International Faculty Development Program. And today's resource person is Dr. Silmani from Morocco. I request our coordinator, Mrs. Durga Kameshwari, to introduce our chief resource person. Ma'am, please.
Thank you, sir. Good evening, everyone. Sri Durga Kameshwari, Assistant Professor in ECE Department. I am very happy to introduce our today's resource person, Dr. Abdellatif SLIMANI, who is working as Assistant Professor in Electrical and Electronics Engineering, Sidi Mohamed Ben Abdellah University in Morocco. He was born in Erfoud, Morocco in 1989. He is a doctor of telecommunications and electronics from Sidi Mohamed Ben Abdellah University, Faculty of Sciences and Technology in Morocco. He received his master's degree in telecommunication and microwave devices from the same university and National School of Applied Sciences in 2013. His research interests include numerical method, array antennas, radar systems, UWB communication systems, RFID systems, and microwave applications. We are very much thankful to you, sir, for accepting our invitation and sharing your knowledge to all our participants. Now I hand over the session to you, sir. So today's topic is microstrip antennas design and problematic. Thank you.
Thank you. Thank you. So I will share with you my screen.
Yes, sir. You can share, sir. You
Okay.
can share.
Okay. Now it's good.
Yes, sir. Perfect, sir. Perfect, sir. Perfect.
Okay. So firstly, I will to thank every person that's associated to organize this webinar conference. Okay, Dr. Aran and all others. So today I will talk about microstrip arrays antennas, design and problemacy. So I will talk about the arts of array antennas, the different kinds of array antennas, the different geometries, the different method of feeding, technique feeding. Okay, so I will finish by the challenge of array antennas. So the plan that will present I will do in this presentation, I will begin by a bibliography, a brief bibliography. Second axis, I will talk about our arts of antenna arrays, and third axis, problematic design that we can face when we need to conceive array antennas, and I will finish by challenges design. Okay, so my academic background in brief. So I have a PhD in telecommunication and electronics since 2080 from Sidi Mohamed bin Abdellah University in Morocco. Also, I have a master's degree in telecommunication and microwave devices in 2013 from the same university in Morocco. So about my research area, I work in numerical methods, arrays antennas, radar systems, ultra-wideband communication systems, RFID systems, and microwave application. About my research work carried out in collaboration, so I have 15 journal people indexed in a lot of Thomson Reuters copies, Web of Science, and I have 21 international conference people. So, arts of antenna array. So antenna array, what does it mean? Array, antenna, or antenna array? So an antenna array is a set of multiple connected antennas which work together to transmit or receive radio waves. So if I have two antennas or more, so I can talk about array antennas or antenna array. Okay, so in antenna array, several single antennas separated from each other are geometrically arranged to give desired radiation characteristic, okay, that are not possible to achieve with a single antenna. Okay, so the question that we can put, why we use these array antennas, why we use array antennas instead of a single antenna. So we have two cases. Okay, so the first case, if I talk about high radiation performance, okay, I talk about high radiation performance. If I talk about high radiation performance, I talk about gain and directivity of our array antenna. I search high directivity and high gain. The second case, if I talk about smart beam steering, okay, I talk here in uh, we call it smart antennas, intelligent antennas, array antennas. Okay, so I have two cases: high radiation performance or smart beam steering. So the question: how can I differentiate between these two cases? How can I differentiate between array antennas that work for high radiation performance and array antennas used for smart beam steering? Okay, so if the first case, if I use a single port of excitation to multiple antennas, I have one single port of excitation for a lot of antennas connected between them. So in this case, I talk about high radiation performance. Okay, I have just one single port of excitation used to connect to power all antennas elements. So for example, here I have in figure 1 linear array antennas. So I have just one port of excitation and one single feed line used to power all antennas elements. Okay, so here I have linear array antennas, and these uh, radiating elements are connected in serial distribution. Okay, I have figure 2 planar array antennas. Okay, 2 2. So here I have also just one port of excitation used to power all antenna elements. Okay, so I talk about high radiation performance in this case. Okay, so to understand the high radiation performance, I give this example. So in figure A, I have just one single antennas, okay, that have a directivity of 3 decibel. Okay, so this antenna, I cannot use it to cover the area of our application. For example, here, a plane or aircraft applications. Okay, so this antenna, that the radiation produced with this antenna, we cannot cover the region of our airplane, okay, or aircrafts. So what I do, I need to conceive to work with another array antennas or array antennas that have high directivity that can cover our area of plane or aircraft. Okay, so in figure B, I have an array antennas with 6 elements. Okay, so I have one beam toward the desired direction, okay, toward the plane, and I have secondary lobes. Okay, so in this array antenna, I have a directivity of 80 decibel. Okay, 80 decibel. So here I talk about high radiation performance. In first case, I have a directivity of 3 decibel but in the second case, I have directivity of 80 decibel, and for this second case, our array antennas can cover airplane in this or aircrafts in this area. Okay, aircrafts application. So when we talk about high radiation performance, I will talk about directivity and gain. Okay, so we have a parameter that we used a lot of in arrays antennas. We can talk about half power beam width. So we use this parameter. We use this parameter to know how our array antenna is directive. Okay, so if we have two arrays antennas, so how we can that the first is more directive than the second. So here we need to know the half power beamwidth. How we can determine this parameter? So if we take the principal beam of our array antennas, so here in red color, okay, so we take the maximum of our radiation and we decrease with 3 decibel. 3 decibel, and decibel we decrease with 3 decibel. But in linear square, we talk about half power beamwidth. Okay, so in decibel we decrease by 3 decibel, and in the intersection of our beam and the 3 decibel give us an angle. So this angle determine our half power beamwidth. Okay, so half power beamwidth is a parameter in degrees. Okay, in degrees. So more this half power beamwidth is small, more the antenna or array antenna is directive. Okay, more half power beamwidth parameter is small, more our array antenna or our antenna is directive. Okay, so we use this parameter to know how much our antenna is directive. The second case, when we talk about beam steering characteristic, okay, so here if we have more than one port of excitation for multiple antennas, okay, so here we talk about a lot of ports of excitation. We talk about smart beam steering. Okay, I give this example. In figure 4, we have hybrid coupler with 2 inputs and 2 outputs. And in figure 5, we have an example of Butler matrix. Okay, we have 4 inputs, first, the second, the third, and the fourth. So we have 4 inputs and we have 4 outputs. Okay, and in each port we have an antenna, a rectangular antenna connected to each port. Okay, so we have 4 inputs and we have 4 outputs, and in the outputs we have antenna connected to this output. Okay, so this Butler matrix is composed of 8 hybrid coupler. Okay, hybrid coupler. So we have the first, the second, the third, the fourth. Okay, here we have two hybrid couplers. Okay, so for Butler matrix, here we have an example of 4 inputs and 4 outputs. We have other example, for example, 8 inputs, 8 outputs, 60 inputs, and or 60 outputs. Okay, so we have a lot of example of Butler matrix. Okay, so here we have a lot of port of excitation, and we have a lot of ports outputs ports. So to understand this example of Butler matrix, I give this example in figure 6. So radiation pattern in Butler matrix. So we have 4 inputs and we have 4 outputs connected to antenna element. Each port is connected to a single antenna element. So if I exit the first port, so I have a radiation performance or main beam toward the direction 1. Okay, if I exit the second port, I have another radiation toward the desired direction 2. If I exit the third port or the fourth port, I have also the radiation toward the direction 3 or 4. Okay, so if I exit the all ports, I have 4 outputs. In the output, we have 4 radiation, 4 beam. Okay, so here we cannot talk about one beam and secondary lobes. like the first example, but we talk about 4 beam that have the same power, okay, the same power. So here, if I exceed each post, I have a desired direction or main beam toward a desired direction, okay. So this is the difference between beam steering and high radiation performance. So I will talk about antenna arrays geometries and feeding techniques. Okay, so the first case, linear patch array antennas. So here in figure 7, we have serial feeding, okay, on linear patch array antenna with serial feeding, okay, single feed line used to power all antenna elements. But in figure 8, we have parallel feeding. We have a part of excitation and we have a lot of feed line used to power all antenna elements. So the difference between these two cases. So for the serial feeding in figure 7, if I change frequency in input ports, if I change frequency, for example, I work in 2.4 gigahertz and I need to work for another application for example, 5 gigahertz. So if I change frequency, the phase shift between antenna element change. Okay, if I change frequency, the phase shifts between antenna elements also change. Okay, but for parallel feeding, if I change frequency, input frequency, the phase shift stays stable. Okay, this is the difference between serial feeding and parallel feeding. If I change frequency in serial feeding, the phase shifts between antenna elements change. But for parallel feeding, the phase shift stays stable when I change frequency. Okay, so this for linear patch array antennas. If I talk about planar patch array antennas, so here an example. So figure 9 serial feeding, we have just one single feed line used to power all antenna elements. Okay, so for figure 10 parallel feeding, so we have just one single port used to power all antenna elements. Okay, so and a lot of feed lines. So also in this case, if I change frequency in serial feeding, the phase shifts between radiating elements change. But for parallel feeding, the phase shifts stay stable when I change frequency. So for circular patch array antennas, another example. So figure 11, we have serial feeding. So we have the excitation and one single feed line used to power all antenna elements. For figure 12, we have parallel feeding. Okay, so at the center of our array antenna, we have the excitation, and each antenna has a single feed line used to power this antenna element. Okay, so now I will talk about the problematic design. So when we need to conserve array antennas, we face always one single problematic. What is this problematic? So we talk about secondary lobes and mutual coupling. Okay, so here we have secondary lobes and here we have mutual coupling in array antennas. Just an example. So to understand this problematic, I give this example. So if I increase the inter-element distance between radiating elements, okay, if I increase the inter-element distance, what happen? If I increase the inter-element distance here, okay, so what happened? I can observe that the mutual coupling between antenna elements decrease. Mutual coupling between antenna elements decrease. So it's an advantage for us, okay? Decreasing of mutual coupling. But the problem that secondary lobes increase. So the secondary lobes is a problem. It's an inconvenience. Okay, why? Because the secondary lobes produce interference with other signals. Okay, interference with other signals. So we search to have just one single beam without secondary lobes. Okay, so the ideal case, we need to have just one single beam without secondary lobes. Okay, so here, if I increase the inter-element distance between radiating elements, I can observe that the mutual coupling decrease is an advantage, but the secondary lobes increase. It's a problem. If we take the second case, I decrease the inter-element distance. Okay, and increase the inter-element distance. What's happened here? The secondary lobes decrease. So it's an advantage. If we talk about secondary lobes, side lobes, so decrease, it's an advantage. But the problem in mutual coupling, if I decrease inter-element distance, the mutual coupling between radiating elements increase. It's a problem because this mutual coupling degrades our radiation, decrease our performance of radiation. Okay, mutual coupling between radiating elements decrease our performance radiation. Okay, so in all cases we have a problem. If I increase the inter-element distance between radiating elements, or when I decrease the inter-element distance between radiating elements. So in our case, we have a problem. So what is the solution? How we can work with array antennas? So for us, what we are doing, we have studied the inter-element distance. We search the best inter-element distance that we can give us a high radiation performance with minimum secondary lobes, and after we search a method or technique used to decrease the mutual coupling between radiating elements. Okay, so the solution. So methodology and calculus. Okay, so we take the linear array antennas, the first example. Okay, we have a linear array antennas, and we have a distance inter element, uniform distance between radiating elements. Okay, so the total field, radiated field in this array antennas equal the superposition of all radiation of all elements. Okay, the total field equal the radiation of the first element plus the second element plus the third, and etc. Okay, so at the end we can find that all total field radiated by this linear array antennas equal R reference at reference multiplied by array factor. So the radiated R reference, we can assume that the radiation at the center of our the reference. Okay, the reference of our array antenna. Array factors equal sinus n psi per 2 divided by sinus psi per 2. Okay, so we can observe that psi equal k multiplied by d sinus theta plus phi. K is the wave or the number, we can talk about constant of propagation or direction of propagation k. Okay, d is the inter-element distance between two antennas. D is the inter-element between two antennas. So I talk about psi. Okay, theta is the angle between the z-axis and the point in the far field, and phi is the phase shift between two successive elements. For example, the first antenna and the second, we have a phase shift. Between the second and the third, we have a phase shift. Okay, a constant phase shift. So phi is the phase shift between two successive antenna elements. Okay, so all total, it depends on array factor, and our array factor depends on distance inter elements and the phase shifts. Okay, k is a constant, and theta is the angle between the points in far field, and z-axis also it's constant. For the second example, when we talk about planar array antennas, so here we have two axes. Axis toward x-axis and we have y-axis. Okay, we talk about planar array antennas. Okay, so we work with same principle. The total field radiated by this planar array antenna is equal to the superposition of all field radiated by all antenna elements. So here we have a reference as the reference, the center of our repair, and we have a term toward x-axis and other terms toward y-axis. So a total equal or as reference multiplied by array factor, and our array factor it depends on x-axis and y-axis. So we have s, x, and s y. Sx equal k dx sinus theta cos phi plus gamma x. Okay. Sy equal k dy sinus theta sinus phi plus gamma y. So Sx and Sy depend of constant of propagation k is a constant depends of distance enter elements in x-axis and y-axis. D distance enter elements between two elements in x-axis and y-axis. Theta and phi is the angles between z-axis and points m in far field, and phi is the angle between x-axis and the projection of points m in x or y plane. Okay. Gamma x is the phase shift between two antenna elements, gamma x and gamma in x-axis, and gamma y is the phase shift between two antenna elements in y-axis. Okay, so we can observe that all total depend on our array factor, and our array factor depends on distance enter elements and phase shifts. The last example, the circular array antennas. Okay, so the same, we work with the same principle. All total field equal the superposition of all radiated field of all antenna elements. So at the end, we can find that of total field radiated equal A as the reference. Okay, multiplied by a term Cn. Okay, so Cn depends on K. Okay, K. So the constant of propagation R. So R here we do not talk about inter element distance, but we talk about radius, because we talk about circular array. So we talk about radius instead of inter element distance. R is the radius of our array antenna. Since theta is the angle between the z-axis and the points m in the far field. Beta more beta n are fast. Okay, so beta n, the angle beta n satisfies the angular position relation. Beta n equal to Pn multiplied by n, and the number of elements at the position n, and n majuscule is the total number of antenna. Okay. Phi in is the phase shift between two antenna elements. Okay, Phi in is the phase shift between two antenna elements. So the directivity of our array antenna. So we will represent the directivity. So before representing directivity, I talk about these terms. Directivity equal the maximum radiation intensity, which equal 1. Okay, and the intensity in the desired direction A0. Okay, so we have 4P Emax divided by P radiated, and P radiated it depends on our array factor, AF, our array factor. So here we have we are doing simulation with MATLAB. So we have started the effects of inter-element distance, D, and the effects of phase shifts on our array antennas. Okay, we add the phase shifts. So the first example here, we have directivity of linear patch array antenna 6.1. Okay, we have a linear array antenna of 6 elements. So the distance enter elements. The first case in black color, they equal lambda per 4. So this is the first inter-element distance that we choose. So we have the maximum radiation toward the angle 90 degree. Okay, we choose that the maximum radiation is toward 90 degree. Okay, toward this direction. So for d equal lambda per 4 in black color, we have just one beam and two secondary lobes. Okay, one beam toward the desired direction and two secondary lobes. So if I increase the inter-element distance, so in pink color, d equal lambda per 3 in pink, okay, in pink color. So what happened? I can observe that the level of radiation increase, okay, increase, and the beam width decrease, okay, in comparison with the first case in black color, okay, the level of radiation increase and the beam width decrease. If I increase this inter-element distance toward lambda pair 2 and red color, okay, and red color, d equal lambda pair 2, what happened? The level of radiation also increase, the beam width decrease, and the secondary lobes increase. Okay, you see that more the inter-element distance increase, more the level of radiation increase, but the secondary lobes also increase. So for the last case, d equal 3 per 4 lambda in blue color. So we have the high level of radiation, but we have in left we have five secondary lobes, or four secondary lobes, and in the left we have four secondary lobes. Okay, so more the inter-element distance increase, more the level of radiation increase, but the problem in terms of secondary lobes. Okay, so here we observe the effects of inter-element distance on radiation performance. We take the second case for phase shift. Okay, so phase shifts. So the first case we take in blue color, we have the phase shift equal 0. We have no phase shift. Phase shift equals 0. Okay, so in blue color, so the the main direction is always toward 90 degrees. Okay, in black color, the first case. In blue color, we have the high radiation is toward the main beam is toward 90 degrees in blue color. So if I change phase shifts to P par 4, okay, in pink color, what happened? I can observe that the direction of propagation change. Just the direction of propagation. If you observe well, so we have about 110 degrees. Okay, so if I change phase shifts, I can observe that that's the direction of propagation has changed, but the level of radiation stays stable. We have no effects on the level of radiation. The phase shifts affects just the radiation direction. We have no effects on the level of radiation. Okay, so also if I change the phase shift toward P per 3 in black color, we can observe that the direction of propagation change, but the level of radiation stay stable. Also for P per 2 in red color. Okay, so the phase shift have no effects on the level of radiation. It changed just the direction of propagation. So we use this technique in intelligent antennas. I can direct my radiation toward the desired direction just by change of phase shifts of our array antennas. Okay. So the second case, I talk about the directivity of planar patch array antenna 6 elements. Okay, 6 elements. So here I choose two direction of propagation. maximal progression toward 0 degrees and toward 180 degrees. Okay, so we talk about just 0 degrees. We talk about the direction 0 degrees. So for the first inter-element distance, dx equal dy equal lambda per 4 in black color. Okay, in black color, we have the the radiation performance. We have one single beam and one secondary lobes. Okay, in black color. If I increase inter-element distance toward lambda per 3 in a red color, what happened? I can observe that the level of radiation increase. Okay, but the number of secondary lobes increase toward 2 secondary lobes. If I take distance inter-element lambda per 2 pink color, what happened? The level of radiation also increase. Okay, but the number of secondary lobes also increase. And for blue color, the x equal 3 per 4 lambda. So I have the high level of radiation, but I have a lot of secondary lobes in comparison by the first case. Okay, so the inter-element distance affects the level of radiation and the number of secondary lobes. So I pass for the directivity of circular patch array antenna, circular patch array antenna. Okay, so here I talk about radius, not inter-element distance. So if I take the first radius equal lambda per 4 in pink color, so I can observe that I have omnidirectional radiation. Okay, I can talk about omnidirectional radiation. Okay, and if I increase the radius toward lambda per 3, what happened? I can observe that the radiation, the level of radiation increase in comparison by the first case. And for r equal lambda per 2 and red color, I have the high radiation, okay, the high level for this case lambda per 2. Okay, if I increase toward lambda 3 per 4 lambda in blue color, I can observe that the radiation decrease in comparison by lambda per 2, and the same for r equal lambda in green color. Okay, so I have the high radiation in r equal lambda per 2 for circular array antenna, lambda per 2. Also, I will start the effect of phase shifts in this array, circular array antenna. So I have phi equal 0 degrees, so I have the radiation performance, the maximum towards 0 degrees and 180 degrees. Okay, so as for us, we choose this direction, 0 degree and 180 degrees. Okay, so if I change the phase shift toward P per 4 or P per 3 or P per 2, I can observe that I have no effects on the phase or on the radiation performance or direction of propagation. Okay, so for this example, if I change phase shifts, I do not have any change on level of radiation or direction of propagation for this type of array antenna, circular patch array antenna. I have no effects on radiation level or direction of propagation. Okay, so in I resume that. So for linear array antennas or planar or circular, so from our studies and the other studies in literature, we can observe that the best inter-element distance that can give us the high radiation with the minimum secondary lobes. So I can talk about lambda per 2. Okay, when we need to conceive an array antennas, so we need to choose lambda part 2 like a distant inter-element between radiating elements, because in this distance I can have an important level of radiation and a minimum secondary loss. Okay, so lambda per 2 is the best inter-element distance that we can use to conceive an array antennas. So if we fix our inter-element distance, we can talk about now the mutual coupling, how we can decrease the mutual coupling between radiating elements. Okay, so for mutual coupling, we have three popular methods. Three popular methods used to decrease the mutual coupling between radiation elements. The first method we can talk about electromagnetic band gap. Okay, OBG structures. OBG structures. So these structures in general are defined as periodic or non-periodic artificial structures which prevents the propagation of electromagnetic waves in a specific frequency band for all angles of incidence and all polarization states. Okay. For the second case, the fixed ground plane. So here we can talk about restrictors in ground plane. We work in ground plane of our array antennas. And split ring resonator. So here we can talk about artificial structures. Artificial structures. So we can discover this method. So the first electromagnetic band gap of structures, we have three structures, three type of structures. The first we can talk about one-dimensional object structures like a holes in the ground plan. Okay, one-dimensional object structures like a holes in ground plane of our array antennas, or this technique we can use for horizon antennas or for filters or for coupler. Okay, so we can use for microwave structures, branched structures, one-dimensional object structures. The first case. The second case, we can talk about two-dimensional object structures. So this structure we have ground plane. Okay, ground plane and the bottom, okay, in the bottom of our array antenna, and we have ovia that's connected between ground plane and the radiating element in the top view. Okay, ovia. So we can consider this method like a mushroom. Okay, like a mushroom. We have ovia between radiating elements and ground plane. So this is the second case of OBG structures. The third case is three-dimensional object structures. So figure A would build structures consisting of square dielectric bars, and B, figure B, or metallic tripod multi-layer network. So for this example, the three-dimensional example, so we can find it in all substrates. In all substrates. The first example, one-dimensional just in ground plan. The second example, we have just two dimension, but for three dimension, we can observe this structure in all substrates, okay, of our arrays antennas. So here we talk about OBG structures. The second case, we can talk about defected ground planes, DGS, defected ground plane, defected ground surface, okay, so, or planes. So here we have a holes or slots in ground plane. So figure A, we have slots between radiating elements in ground plane. The second figure B, meander line under each radiating element. Figure C, different slots under the radiating elements, and figure D, we have different form of dumbbells in ground plane. Okay, so here we have different slots in ground plane. We work in the ground plane. The last example we can talk about split ring resonator, SRR. Okay, so in the natural materials we have permittivity and permeability are superior to 0. Okay, so the natural material in the natural material we have of permittivity and permeability are superior to 0. Okay, so we have A, H, and K. Okay, so K equal O, A, vectorial H. So we have the direction of propagation toward K. Okay, toward K. The electric field depend on permittivity, and the magnetic field H depend on permeability. Okay, so if these two parameters, permeability and permittivity and permeability, has the same sign, so we can have the propagation, okay, the transmission. So for this example, or for the third example, double negative materials. So if epsilon and mu are inferior at 0 or superior at 0, we can have the transmission in our array antennas. So if we have different sign of between permittivity and permeability, if we have different signs, so here we cannot have transmission. If we put a structure in or between radiating element that has a different sign of permeability and permittivity, so we cannot find transmission. We can decrease the transmission, okay, in our structure. So this is the technique that we can use in split ring resonator. We can create material with opposite sign, and we put it on our array antennas to decrease the transmission between radiating elements. So here we have an example. Figure A, we have a rectangular SRR split ring resonator. B, modified SRR. C, resonator with 3 spiral turn. So we have the first spiral, the second spiral, and the third spiral. Okay. And D, Hilbert's fractal curve. So we can use this technique for the last technique D, we can use for fractal antennas or rise antennas, fractal or rise antennas. So this is in figure 29 SRS structure for an array antenna. We have monopole antenna of 2 elements. Okay, so we use SRR inclusion between 2 antenna elements to decrease mutual coupling between these 2 antenna elements. Okay. So for us, we have an example that we are doing in our laboratory. Example of simulation, okay, of object structures. So to understand that, so this is the structure that we conceive in our laboratory. We have a resistive metal, okay, resistive metal with cutted face, okay. So we have the R is impedance, rho is the resistivity, and R and S are dimensions, surface and length. So from dimensions of our structures and the impedance, we can find the resistivity. So we can assume that the impedance of our structures equal 50 ohm, okay, equal 50 ohm, because we work with a generator of 50 ohm. So from 50 ohm and dimensions of our structures, we can know the nature of our structures. Okay, so we can find that our structures have a resistivity equal 60, 90 pounds or 79 pounds 94 multiplied by 10 in power 13 ohm meter. Okay, so this is our proposed object structures. So here we have an example of simulation. The first figure A, we have our array antennas without any structures, and figure B, the array antenna after putting the object structure. So figure 31, we have the transmission parameters before and after the put of our object structures. And figure 32, we have S parameter, return loss of our horizon antenna. So we can observe that when we put the OBG structures, we can observe that the transmission between these two ports, the first port and the second port, decrease. Okay, also the matching in our array antenna is improved. Okay, so before and after putting the OBG sequence, we can observe that we have an amelioration and improvement of our parameters S12 or S11. Other parameters is the surface of file distribution. So figure 33, we of file before OBG selectors, okay, and figure 34, we of file after OBG selectors. So for figure 33, okay, so the maximum radiation is equal 70.577 volt per millimeter. Okay, so this is the maximum level. But if we put the structures, OBG structures, what happened here? We can observe that the radiation, the off-file distribution increased toward 25.786 volt per millimeter with a difference of 8.209 volt per millimeter. Okay, we can observe that we have an improvement of file distribution in our array antennas after putting OBG structures. The second example, we have a planar array antennas. So we have here 2 ports of excitation to study the transmission between these 2 ports. Okay, so we have planar array antennas with and without OBG selectors. So S parameters. So figure 36, we have the transmission coefficient before and after putting OBG selectors, and figure 37, we have S11 parameter before and after putting OBG selectors. So we can observe that when we put OBG selectors, the transmission decrease and the matching between in our array antenna is improved also. Okay. Also for surface file distribution. So for the first case, figure 38, we have a file before OBG selectors. So the maximum surface of file equal 60 pounds 808 volts per millimeter. So figure 39, we have a file after OBG selectors. So the maximum of file is equal 21 pounds 172 volts per millimeter with a difference in comparison with the first case of 4 pounds 364 volts per millimeter. So we can observe that we have an improvement of file distribution after OBG selectors. Okay, so now I talk about challenges design. So this is the last axis. Okay, so the challenges design in arrays antennas. So about challenges design, we can talk about the compact and low profile. So we search to have a miniaturized structures. We talk about dimensions. More our structures is more miniaturized, more this structure is best. Okay, so miniaturization, we talk about miniaturization of array antennas. The second case, I talk about high radiation performance. So if I have array antennas with 20 decibel is more than antenna that have 10 decibel. Okay, so I talk about high radiation performance. Okay, I search the high radiation performance. So more the number of antenna elements decrease, more the radiation performance decrease. More the number of radiating elements of antenna increase more, the radiation performance increase. If I have 10 antennas, is better than 5 antennas in array. Okay, so to have a high radiation performance, I need to have a lot of more antennas. The third case, I talk about low mutual coupling. Okay, so I talk about mutual coupling. So we have three popular methods used to decrease the mutual coupling between radiating elements. We have OPG restrictors, we have split ring resonator, okay, and we have the defixed ground plane, DGS restrictors. Flexibility, we talk about flexible antennas that we can put at on any structures, any circuits. Okay, we talk about flexible antennas or arrays antennas. Configuration and orientation. So configuration, I talk about frequency, frequency, resonance frequency or frequency of function. Okay, so frequency. If I have array antenna that's function for 3 or 4, frequency is more than antenna that's function for just one single frequency. For example, I have antenna that function for 1 gigahertz, 2 gigahertz, 3 gigahertz, and 4 gigahertz. So this antenna I can use is for a lot of application. But for one antenna that has just one single frequency of operation, for example, 1 gigahertz. So this antenna I cannot use for for other applications. Okay, so I talk about a configuration of frequency. Okay, orientation, I talk about radiation. I can direct my radiation toward the desired direction just by change of phase shifts. Okay, so I talk about orientation. Multi-modes operation. So here I talk about TA and TM modes. Okay, TO and TM modes, and I can talk about polarization, vertical or horizontal or circular polarization. If I have array antenna that can function for this polarization, vertical, horizontal, or and circular is more than antenna that function just for one single mode. Multiple frequency bands. Okay, so here for configuration, I talk about frequency, and for this last axis, I talk about multiple frequency bands. So if I have array antennas that function for a lot of bands, is best than antenna or array antennas that function just for one single band. Okay, so for example, I have array antenna that function for wideband application and ultra wideband application and 5G application. So this array antenna is better than array antenna that's function just for one single band. Okay, so I finish for this presentation. So for any question, you can contact me on my mail abdellatif.slimani@ucmba.ac.mi, and you can subscribe or you can just watch our video on our channel. I have our channel with other colleagues. We work on all we work in area of telecommunication. Okay, so we have this channel on YouTube, Tafilalt for engineering. So we put I put with other colleagues some videos in telecommunications and antennas, microwave devices. Okay, so thank you for your attention, and welcome to your question.
Thank you, sir. We
Thank
have a
you.
question for one of the participants, and that is, can you explain something about leaky dielectric materials? It is there in the chat box as well. You can see that. Hello, sir. Sir, we are unable to hear your voice, sir. Hello, sir. Sir, we cannot hear you. Yeah, yeah.
Hello?
Yes, sir.
Yes, you hear me now?
Yes, sir. Yes, sir.
Okay. So for the question leaky dielectric, sorry, this I don't see these terms leaky dielectric before, but I can search for it. Leaky dielectric. I don't know leaky dielectric, so I can search for it and I can send Mr. Aran. Okay.
Okay, sir. One more question. It is there in the chat box as well. What type of antennas are used in today's radar systems?
So type of antennas, it depends on application. Okay, it depends on application. So for example, if we talk about radar system used for uh, for radars for near distance, we can talk about microstrip horizon antennas. Okay, for near distance radars used for to cover near distance, for example, for police. Okay, radar police. So we can talk about microstrip horizon antennas.
Okay, sir. Thank you very much, sir, for
Okay.
spending your time with all our participants and sharing your knowledge. And we are very grateful to you for accepting our invitation. Thank you very much for gracing the session, sir. Thank you.
Thank you very much. Thank you. Thank you.
I request all the participants to fill the feedback form, and tomorrow the session will start at 10:30 a.m. sharply. Thank you.
Thank you very much. Thank you.
Sir, you can leave the meeting, sir.
I can leave.
Yes, sir.
Okay. Thank you very much, and thank you for all persons. Okay. Thank you.